Hey everyone. I hope that the exam went well for all of you guys. The reason I didn't upload a video last week is because I thought that you guys would be more focused on the exam than worrying about the new action centers. So this week is going to be sort of two action centers put together, 8 and 9, because 9 is really short, and it's not much new material per se. And so 8 is about carbohydrates, and so the most important thing for that is just like learning these monosaccharides and like the aldoses and the ketoses, and it's really intimidating to look at and everything, but if you draw these out like 2 or 3 times a day, you'll start seeing the pattern, and you'll be able to do these really quickly. You'll work with glucose so much in this class that you'll get to a point where you'll be able to draw glucose in your sleep. It ends up happening inevitably. The couple things I do want to point out though, this is, I think, is really important, that for the aldose is the number of carbons -2 is the number of chiral centers that you have. For the ketoses, the number of carbons -3 is the number of chiral centers you have. And the last thing, I guess, is just I would know these linkages for sucrose, lactose, maltose, and glycogen. I think those are some of the things that he would have covered in the slides that he could expect you to have memorized for an exam. But he should have gone over, the pattern, how to read these, and so I'm not going to go super in depth into those things, and you'll see me explain problems related to these in the action center questions, so they should be fairly self-explanatory whenever I talk about like the terminology related to this. And so the first one is this one asking if N-acetyl beta-D-glucosamine is a reducing sugar. And we have this information that the N-acetyl group is attached to carbon 2. So I think that the first step here is just to draw glucose, which, is, so 1, 2, 3, 4, 5, 6. This is a CH2OH. And then for glucose, I've got an OH on the right, on the left, and then 2 on the right. So what's happening here is that he's saying that we're modifying C2 somehow. This hydroxyl group is going to be modified, and I'm just going to call it R for now. And that R doesn't interfere with this, I guess it's an intramolecular hemiacetal reaction, where this OH group will attack that carbon to make the ring form. So because that can still happen, because we haven't changed carbon 1, that aldehyde carbon, this is a reducing sugar. Because it can undergo that cyclization. And once it does that, just in case you were curious, N-acetyl beta-D-glucosamine, it's going to look something like this. Basically, you're going to have an N with an acetyl group attached to it. And then the rest of the glucose will be, you can think about it as you would normally. Like that. And you don't need to know that. That's just for fun, I guess. So this is similar, but over here he's asking about D-gluconate. And so if I draw D-gluconate, it'll look similar to my glucose, but he's saying that, the C1 is oxidized to this carboxyl group. So instead of an aldehyde there, we have a carboxyl, and then we have, glucose as normal. So the important thing to recognize here is just that, okay, so we modified C1, and we modified it such that, this is its most oxidized form. This isn't going to be able to do, this reaction anymore, so it's not going to be able to reduce something else if this first carbon is already in its most oxidized form. So because we modified, I guess a good way to think about this is because we modified C1, this is not a reducing sugar. All right. And now the last one I wanted to do from this is actually, so you're going to see this question a lot, especially if you had him for organic 1. You're probably familiar with this type of question. This is just one of the possible ways he could ask this to you in biochemistry. And so he's saying that, this is just a fancy KEQ, like delta G question. And so the way that I always like to do these is I like to start out with, the equation that I'm working with, and I like to draw the graph first. So what he's saying is that, if I have a graph and I have, delta G not here, and then this is the reaction coordinate, then what ends up happening is that my curve is going to look like this, where the boat form is higher in energy than the chair form. And so, between these values, my delta G is negative 6.37 kcal per mole. So my KEQ is the concentration of the chair over the concentration of the boat, because this was my initial equation that I put into that KEQ form. And so once I do that, this turns into, I can plug this into my delta G naught is equal to negative RT ln KEQ. And I know delta G, which is negative 6.37. I also know RT, which, are negative 0.001987 times the temperature, which is 298 ln of KEQ. So if I solve this out, what I end up getting is that KEQ is equal to 997. And so I've solved for KEQ in the form of, this KEQ. So that means that there are 46,997 chairs for every one boat. And so that is my ratio that he's asking for in the question. And that makes sense if you think about it, just because, you'd expect to have way more of the more stable thing. And in this case, that's chairs. And so now we can move on to action setter 9. And so this first question is asking about, biochemical standard free energy change. And the reason that he's doing this is just because he wants you to get started thinking about these kind of redox reactions that you're going to see a lot when you go to metabolism. And eventually you will memorize, what this reaction actually means, like why it's significant that we're making oxaloacetate from malate, or malate from oxaloacetate, those kind of things. And so these are good precursor to that discussion of metabolism. So I've already listed the reduction potentials here from the textbook. And so we're looking for the delta G naught prime value for this reaction. And so based on the reaction potentials that I have, I know that I'm going to need to flip my top one because oxaloacetate is a reactant here and it's a product here. So I'll flip that one and I'll say the L-malate to oxaloacetate plus the 2H plus, or I'm sorry, 2E minus plus 2H plus. That has this delta E naught prime value of, instead of negative 0.17, I'll be positive 0.17 here. And then the bottom equation can stay the same, NAD plus 2E minus plus H plus going to NADH. And my delta E naught prime, that's going to be the same at negative 0.32. So when you do this equation, the electrons will cancel out, this hydrogen will go away, you'll have one H plus left over here. And then, we get our net reaction of L malate plus NAD plus goes to oxaloacetate plus NADH plus an H plus. And then we add down our delta E naught, we get negative 0.15 volts. And that negative 0.15 volts we can plug into our equation. Delta G naught prime is equal to negative N times Faraday's constant times the delta E naught prime. And so we do that, and there are two electrons being exchanged in this reaction, so negative N is negative 2, Faraday's constant 23.1, and then my delta E naught prime that I just solved for is negative 0.15. So we do that, and we get 6.93, whoops, that's not very good, 6.93 kcal per mole for that reaction. Next question is really similar. I just wanted to go over it because he does some weird things with units here. Basically, it's another Hess's law question where you just have to add these reactions in a specific way. And so, he's asking for the heat of meter rotation for, you want your equations to add up to solid alpha D glucose to solid beta D glucose. But you do want your answer, and just pay attention to these things when you do these questions. He wants your answer in terms of kcal per mole, and he's given you all of these values in joules per mole. And so the way that I would start this is like I actually rewrite everything out when I do these, but you don't necessarily need to do that here because the way that he's written them, if you added these straight down, alpha D glucose cancels out here. Like if I add them straight down like this, so alpha D glucose cancels with alpha D glucose here, and then the beta cancels out as well. So what you're left with is this alpha D glucose, that solid, going to beta D glucose, also the solid. And then if you added those delta H's down as well, you would get 4,874 joules per mole. And so now, the thing that you actually need to, the step that's, a lot of people forget with this question is just converting it to kcal. So 4,874 joules per 1 mole. So 1 calorie is 4.18 joules, and then 1 kcal is 1,000 calories. So the joules cancel here, the calories cancel there, mole stays the same, and we get 1.166 kcal per mole. And so that's going to be it for this week, or for the last 2 weeks. I know that it probably seemed pretty fast, but the main thing I think for these is it's really all contingent on your knowledge of these sugars. And I don't know, I might make like a separate video just to go over how to memorize the sugars and like how to visualize them properly, because I know that that's a little bit challenging to do when you start out, like, visualizing the actual standard notation from one of these line structures and just manipulating even the standard notation in your head, and like how the hemiacetal reactions work and all those kind of things. So let me know if you want me to make a video, just focusing on, I guess, strategies that I use to memorize things like this, and how I, manipulate the sugars around in my head. Yeah, so that's it for now. Let me know if you want to see a video like that.